about differentiability, and differentiability at a point is the first thing that we're going to consider, and a function is differentiable at x when its derivative exists at x. So it has a slope at x. And then we'll also talk about differentiability on an interval. And so a function is differentiable on an open interval from a to b when it is differentiable at every point in the interval. And one of the most important things that you can remember about differentiability is a function must be continuous. In order to be differentiable. And so, if you have any type of discontinuity, if you have a hole in the graph, if you have a jump, if you have a vertical asymptote, then the function is not differentiable at that point. It has to be continuous first before you can even check to see if it's differentiable. So for this, you don't necessarily have to graph it. I've got the graph here. Probably just put the equation, so f of x equals the absolute value of x plus 3. But we'll look at the graph here. So whenever we talk about the derivative is the slope of the graph. And so for an absolute value function, if I look at f prime of negative 5 is right here, so we'd be looking at this point right here on the graph. So f prime of negative 5, we're not looking at the y value for that. That'd be f of negative 5. We're looking at the slope of the line there. So when I look at that one, Destiny, what's the slope of that line going through that point? Almost. It's not going to be 1, but it's decreasing, so it's going to be negative 1. Okay, so the slope is going to be negative 1 at that point. Yes, sir. We'll find you something else to watch, okay? Oh, good. I'm so glad. Watch the monkey if you want. Okay. But all of you who are absent, I apologize. Henry is here with us, and these notes might be a little crazy. All right, so at f of 0, we're talking about this point right here. Just as what's the slope of the graph at this point right here? It's 1. Okay? And so this would be pretty easy to answer for any point except for C. And so at C, whenever I look at that graph, that's the turning point of the graph. And answering that question is not very easy. You're all done with the computer? Okay, you can shut it. Do you want the color? You want to learn calculus? No. They don't need this today, but Henry, you can't shut it now. It's not gonna come back up good. Okay. So at this point right here, you can't really tell the slope because on the left side the slope is negative 1, but on the right side the slope is positive 1, and so this just does not work out here. So this derivative does not exist, and we talked a little bit about this the other day. Okay, so this is really important to remember. Functions are not differentiable at sharp turns, and another a fancy word for the sharp turn is a cusp. I think AP will accept that as a reason. If it asks for differentiability and it gives you a graph, they'll accept it's not differentiable at x equals -3 because there's a sharp turn, or you could use the fancy word cusp. Alright, questions? So if you're asked to tell differentiability from a graph, you're basically looking for two things. If it's not continuous, it's not differentiable at that point. So that'd be holes, jumps, or vertical asymptotes. And then if you have any sharp turns in the graph, it's also not differentiable at those points as well. Okay, let me get it. For a function to be differentiable at a point, x equals a, f of x, or I guess f of x must be continuous. I guess at x equals a. Okay, good. So f of x has to be continuous at that point first. That's what you've got to check first. And then your derivative has to be the same on the left side and the right side. So your slope has to be the same on the left side and the right side. So for this, we'll say that the limit as x approaches a from the left of f of x minus f of a all over x minus a. And if this, we can think of this part right here is f prime of a from the left. That must equal limit as x approaches a from the right of f of x minus f of a all over x minus a. And this would be the derivative at a from the right. So, these two things have to be true in order for the function to be differentiable. Remember, for continuous, you have to say something's continuous, the limit must exist, the function must exist, and they have to be equal to each other. For it to be differentiable, all those have to be true, plus the slope from the left, or the derivative from the left, has to equal the derivatives from the right. Thank you, Lily. So, here is an example. I'll let you copy that down there. Those are, yes sir, the plus sign right there. If you're all done, yes, they probably take off if you don't watch the entire video. So that might hurt you a little. Uh-huh. Mhm. You got to get like a certain level first before you get paid anything, but you. Right. Right. So. Mhm. Yeah. 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 Okay, so back to this one. Alright, so the first thing that you would want to check before you even start to think about whether or not this is differentiable is with the microphone. Okay. Okay, they go over here. You can come back. Over here. You'll see the other ones. Okay. See the other ones over there? On that bookshelf, yeah. You can just set them there. That's fine. Okay. So, we would check for continuity. So if we did the limit as x approaches 0, and the only place this is going to have a problem is at 0. Limit as x approaches 0 of f of x from the left, that would be 0 plus 1, which would equal 1. Oh. Equal 1. And then if we do the limit as x approaches 0 from the right of f of x, that would be 0 plus 1 squared. That's also going to be 1. So this function is continuous at f of x. If you want to use a calculator, you can get one. Yeah, okay, get one. And so this one is continuous, so we can proceed with checking differentiability. So what we would have to do is we would do the limit as x approaches 0 from the left. And so if we're doing the limit as x approaches 0 from the left, we're using that top function. So we would do f of x, which would be x plus 1, minus f of 0, which in this case, using that left function, that would be 1, all over x minus 0. And so if we do that, what did you find, Henry? Yeah, we'd get x. Oh, it should still have limits. Oh, he'll think he is. It'd be nice to go back to being a kid where value of money didn't matter, just the amount. Like I could trade him 2 $1 bills for $100 bill, and he'd be happy with the $2 bills. So we've got limit as x approaches 0 of, it'd be x over x, which is really just 1. So you're going to get a limit of 1 from the left. So that tells you that f prime of 0 from the left. Uh-huh. That's 1. You want to help me teach? Come on up here. Come on up here. Okay. All right, we got to teach them about limits, okay? Can you tell them about them? You can't? Okay. All right. So I'll tell them then, okay? Okay. And then so if you do limit definition of derivative as x approaches 0 from the right, it's the same formula, the f of x minus f of a over x minus a, but we're using that bottom function. So we would have x plus 1 squared minus, and then we'd have, if we plugged in 0 here, we'd get 1 all over x minus 0. So that would give us the limit as, we can't do that right. Uh-huh. Yeah, I gotta work on this. You going over there now? Okay. Alright, so you would have x squared plus 2x plus 1 minus 1 all over x. And that would give you the limit as x approaches 0 from the left of x squared plus 2x over x. And you could factor out an x out of that numerator, so you'd have x times x plus 2 all over x. These would cancel, and you would get 0 plus 2, which is going to equal 2. So in this case, the function is continuous, but it is not differentiable, because whenever you take the derivative from the left, you get something that's the derivative from the right. So this would be not differentiable. At x equals 0. And if we just graph that really quick to see what it looks like, here, we would have just x, y equals x minus 1, but that would only be for x is less than 0. And then we would have y equals x minus, it was a plus, wasn't it? Plus y equals x plus 1 squared, but we would only use that one for x greater than 0. And so you can see that those two meet up, but they're not, it's not a smooth curve. So like, especially the more you zoom in, you can tell like that is a sharp turn in the graph. It's not just a smooth curve there. So that would be a place where the graph is not differentiable. So, this is where I had to go pick up Henry, and let's see. We might have done enough. Let's do one more, and we'll use a graph. So let's say, I'll write it. Let's do example. What is this example? I haven't been numbered them anyway. We'll just call it example. F of x equals for x is less than or equal to -2, and let's do sit one again.
I got some money.
Oh, goodness, you gonna buy me something with it?
No. I want some my money.
Can I have a little bit?
No.
Are you gonna share it with them?
No.
No. Okay. Alright. Okay, so I think this is what I'm wanting. So square root of negative x plus 2 plus 3.
Plus.
And yeah, okay. So with these types of problems, some of the ones you're gonna have on your homework say that you can use a graphing utility to decide where this is or is not differentiable. So if we're going to use a graphing utility, I like Desmos better than anything for these because I think it is the easiest to deal with. Let's see this graph, Henry. Let me show you. Look, I'm going to just type it in and it'll show up. It's going to be pretty cool. Alright, watch that. do a piecewise function here, but if you just need to see the graph, this is good enough. Oh. Okay, there we go. That graph's showing up. And then we're going to have y equals x squared plus 2x plus 3. And oh, I'm sorry, I was squishing it.
This is my money's the mayor.
Silly mama.
Silly mommy.
Okay. Oh, I know what it is. Let's. Okay, so if the problem was like this, because I was not doing this correctly in my head. So if it was like this, would this be differentiable? It would not be, because it's not even connected right there. So you have a discontinuity. So that would be a no. I really wanted it to be at least continuous, so I could fix this by. Okay. I could fix this by making that plus 1 instead, like I wanted it to be. So if I did a plus 1, then you can see that it'd be connected there. So in this case, I can tell that it's now continuous. Is it going to be differentiable? It's not differentiable at this point, because you can just see, Henry, is that your calculator? It's not. It's Wendy's. Don't you break Wendy's calculator, but here, this is not differentiable because you have a sharp turn. So you'll have some that you just have to look at, like that. I'm going to go ahead and show you this on the calculator too. You got the water? Okay. Yeah, you can drink that water. That's yours. I'm going to go ahead and show you this on the calculator also. If you get one that you're unsure about, let me show you how to do this on the calculator. The calculator will take a derivative for you. Okay, so on the calculator, now in this case, if you put it in as f of x, it wouldn't work so great. But so a derivative. No, they're not calling you. Nobody's calling you, Henry. Put it back. Put it back. Okay, you put it back. Derivative on the calculator. Alright, so if you want to take a derivative on the calculator, you do F3. Alright, Henry, you gotta put it up before you break the phone. I'll cut wood and talk to him for a while. He's probably down to the he's probably down to the field. He's probably not even still up here. But Henry, you gotta put it up. Okay. Coming up here to help me? I need your help again. Okay. Let's show him how to use his calculator right here. Tell them if they want to do a derivative. No, yeah, okay. So you're going to press F3, and you're going to differentiate. And then you'll have to do each part separate here. But you'll just type in the equation. So square root of negative x plus 2 plus 1. And you have to do comma x. And then if you hit enter, it'll take the derivative for you. a whole lot quicker than the limit definition of a derivative, especially for these harder ones. So I'll take the derivative. But there's an even better feature here. So you got to type in the equation, you put comma x, and then you close your parentheses. And so if after you do the derivative, there is a key right here that is, you want to get in?
No, I want to say.
Okay, you can go. There is a key right here below the equal sign that just looks like a bar, and that bar is a mathematical symbol that means such that. So if you put x equals -2, it'll go ahead and plug that number in for you. So the slope on the left here would be -1/4, which looks about right from the graph.
I don't like them.
And then you can do the derivative from the right, so we could do the x squared plus 2x plus 3. Did you even close it? Comma x. So that's the derivative, but if you just want to plug, here you can plug number in pretty easy. 2 times -2 plus 2 would give you -2, or you could do the such that x equals, x equals -2. And so you can see the slope on the right side is -2. This one's really obvious that those two do not have the same slope from the side, so you wouldn't necessarily need to do that. But if you got ones that looks like they were pretty close, you might want to check it. No, you can't have that. No, you can't. Do you want to draw a picture on the board? I think they'd like to see your colors. Alright, so those scissors are too sharp, you can't use those. I got some you can use. Okay, so your assignment. I'm going to get you some. Hold on. It's going to be on page 133. And we are going to do we're going to do 75 through 84. The first one, 75 through 78, those are with a calculator. The one 79 through 84, those, I want you to try those without a calculator. 79 is the absolute value. Just think of what the graph looks like for absolute value. You won't do those algebraically, just think of the graph for those. For number 80, that one is just going to be a equation. That one. Actually, let's say 81. Let's just do this. 81 through 84. Do those without a calculator. I'm going to let you without calculator for that. The others, you just use the calculator or Desmos. Desmos is easy.